Good evening. It's Sunday night around 7 o'clock. And I do these things once in a while where I just get on the camera and do something that interests me. Basically, I do something related to one of my classes. This semester, I'm teaching 4 classes. I'm doing second semester Java programming. I'm doing discrete structures, system programming in C, and a SQL database course. And so tonight I thought I would just doodle around and do some stuff with finite state automatons, which is the topic in the discrete structures right now. We're heading into the Thanksgiving weekend here in the United States, so I know a lot of the students are thinking about finals coming up in a few weeks. So I thought I would just doodle around tonight and wait till see if somebody requests for something for me to do. So just a little recap of what we learned this week. We were talking about finite state machines, finite state automatas, and just some terminology, if I can write here. We have an alphabet, which is a set of symbols. So an example of that might be like the set of A, B, C, and D, which means these are the only symbols that our finite state machine works on. It could be anything else. It could be like, fish, star, box, and circle. Pretty much any set of symbols that you want to accept in your finite state machine. And then a string is any concatenation of those symbols. So an example of a string on the alphabet A, B, C, D might be B, A, C, C, A, or A, B, C, D, or maybe just B, or actually it could even be nothing. The empty string, which we represent using the epsilon character, that just means there's essentially no string there. And then a language, let's see, is the set of all the possible strings that you want to accept. And this set could be finite in size. It could be just a few things in it. There could be many things in it. There could even be an infinite number of strings. You can create a finite state machine that accepts an infinite number of strings, but they still follow a specific pattern. Okay, and then we talk about a regular language. And a regular language is the specific set of strings that a finite state machine accepts. And I guess the point should be made that regular languages aren't all languages. There are languages, there are sets of strings that a finite state machine can't accept. For example, if you wanted to accept all the strings in which the number of parentheses were correctly balanced, which would be useful in like a programming language, a regular language cannot do that, or that's not something that a regular language can do, or a finite state machine can do. Something else like being able to count, or being able to do operations like adding two strings that represent numbers together. A finite state machine can't do that in general. Now, actually, a finite state machine can do very specific operations, like it's possible to construct one that can just add 1 to a binary string. So if you have a string of just like ones and zeros, you can construct a finite state machine that just adds 1. It's possible to do that, but it's not possible to, say, take 2 strings and like add them together. All right. I think that's it for the terminology. Go to the next page. I guess we could start by just making some state machines. And by the way, on your screen, if you're watching this on a web browser or on a desktop computer, you should be able to see a chat on the sidebar, a chat window. If you're watching this on a mobile device, I don't think you can see that, but if you're watching on a laptop or a desktop, you can see that. So I'm going to type in there. And then if you have any requests for me, just let me know in chat and I'll see if I can work on that. So a finite state machine or a finite state, you know what? The proper term is finite state automata, but for some reason that doesn't roll off my tongue like finite state machine does. So you usually hear me say finite state machine, and I really mean the correct term. So a finite state machine, you have a set of states, which we represent with a circle, and we have a set of transitions. So I'm going to draw in a few states here. And some transitions, which are really just edges on a graph, and they're always directed edges. And one of the states is labeled the start state. So we do that by drawing an arrow pointing to it. And then one or more of the states are designated an accepting state. And I say one or more because it's possible to have multiples. But the accepting states are drawn with a double circle. And then also for ease of talking about these states, we like to label them. You can label them with like 1, 2, 3 or A, B, C, D. I like to use numbers. So here's 1, here's 2, and here's 3. And then we're going to label each of the transitions with a symbol out of our alphabet. And I'm going to say here that our alphabet is, say, the set of A and B. So I'm only going to use the letters A and B. So here's A here, here's B here, and there's A here. And let's do another transition up here, and let's label that with B. Okay. And I hope you can see why I had to put in that transition, because I didn't want to get stuck down there in state number 3 and then not be able to get back to state number 2. Okay, and so now the question is, what strings, or let me back up and say, what is the language that this machine accepts? That is, what are all the strings? So one of them is just A, and you can do that by just starting at 1 and going zip over here to 2, and then you're done. Another one would be, how about, let's do B and, BB. And you can do that by starting here at 1, going down to 3, and then up to 2. Let's see, what would be another one? We could do A, B. So that one starts at number 1. We go across to number 2. And since we're not done with the string yet, we're not going to stop on this accepting state. We're going to keep going. So we go down to number 3 and then up to number 2 again. Let's see, what would be another one? We could do B, A, B. So we start here number 1. We go B, A, B. And you want to do some more? I mean, you can probably see there's an infinite number of strings that this machine accepts because of the looping that goes back to number 2 over and over again. So I'll just say there's more. So essentially this set is infinite. And one thing we might want to know is, what is the regular expression? that represents this finite state machine. So let's see if we can figure it out. We start on 1. Actually, what we do is we kind of look at our language and we see if there's any patterns in there. What I see is that it looks like if we start here and we go down the A branch, then the only way to get back to the accepting state is to go A, B. So starting in here, we go A and then A, B as many times as we need. The other way is to start here at number 1 and go B, and then go B, A, B as many times as we need. You see that? Start at 1 and go B, and then B, A, B. And then A, B, A, B, A, B. All right, so I think that gives us what we need. So it's either, let's see, it's A or B, B, followed by A, B, star. I think that's right. So it's, let's see, it's an A followed by 0 or more ABs. So you can either choose to do the loop or not. Zip back over here and you can go down the B route and then a B again. So that gets you to the accepting state. And then as many ABs as you need. So I think that's a pretty good regular expression. Another way we could do it is we could say A, B, star, or B, B, A, B, and then we'll put that in parentheses like that. So either you choose to start going down the A, what am I saying? Like go down the A road and then you go A, Bs, or you go down the B road and then you got to do another B and then you can do as many A, Bs as you want. But you can see how the bottom one is kind of equivalent to the top one. If I just think about factoring out the A, B star, then you get the top one. All right, let's see, should we maybe do another one? All right. So I'm just gonna, like I said, I'm just gonna doodle around and see what we come up with here. So here's our starting state, and I'll put in a few more. Oh, I need to say our alphabet is, let's do X, Y, and Z. X, Y, and I'm going to put in 2 accepting states on this one. Let's see, I'll do Z goes across, and we had a request to do 2 ending states, so that's exactly what I'm doing right here. Let's go across this way, and we'll do an X, and let's go up this way, and we'll do another Y. And then I want to introduce some kind of loop in this, so I'm trying to figure out what to do. Oh, let's do like a loop here. We'll do Z. And then we'll do a Y there. That's probably good enough. Okay, so what's the language? What are all the strings this thing accepts? Let's see, one of them would be start here at the first one and just go across with an X to go over here. And that would be one of the strings that we accept. Let's see, another one would be to start here and follow a Z and go over here. And then go to the accepting. Let's see, what would be another one? We could go Y, X, and get down to this one down here. Y, X. And we start here. We go Y, Y, and get up to that one. Okay, now it gets more complicated. So we can go y, x, and then yx, yx, yx. So we can do yx. This is kind of similar to the previous one. We do yx, and then we can do a bunch of yx's. So we did a yx, that gets us the accepting state, but then we can do yx, 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 da da da. Okay, what's another one? We do y, and then as many z's as we need, and then an x. So y, z, 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 x. That'll do it. And here's one, y, z, 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 x, and then y, x, y, x. And what's another one? Oh, we could start here at the top one. We could go down here, do a bunch of z's, and then go y and get up there. So we could do y, bunch of z's, and then y, and then we're done. We could also do y, x, y, y. That one is here. Start here. Go y, x, y, y. And I hope you can see that there's an infinite number of strings here because of the loops. Now, regular expression. This is going to be harder. So I'm going to take a stab at this. So if across the top, we've got x. Let's do it this way. I can take off the parentheses. X or y. Oh, sorry, not y. Z. So that covers the top two. Or y, z star, y. Okay, that covers this case. So what I'm doing is I'm just kind of writing them all down. Then we got y, z star, x. And that gets us across the bottom, followed by yx star. Because then we can do z's also. Well, let's write down another case. Y, let's see, y. See, what I'm trying to do is I'm trying to work in the z star and the yx's together. So I think we got to do it like this. This is tricky. Let's see, z star x. Man. See, this is the problem here, is that trying to just derive a regular expression from a fairly complicated finite state machine is a little tricky. And that's something we were working towards in the class, which was how can we kind of do this in a manner where we're following an algorithm, following a procedure to derive the regular expression. Your way through it this way, but it sometimes works a little bit better to follow the algorithm. And we're going to get to that here pretty shortly. All right, so I'm kind of going to give up on that one because that looks a little tricky. Let's see, y, z. Yeah, I don't want to do that one. If you could figure that one out, let me know. All right, so all of these so far have been examples of deterministic finite state automaton, or DFA. Okay, so with a deterministic finite state automaton, there is one transition for each symbol per state. So, for example, if your alphabet is ABC and you've got a state, then you're going to have at most one transition out of the state for each symbol. And I should point out that there's a little bit of a differing opinion about the definition here. Is that some people would say there needs to be exactly one transition for each symbol. So if your alphabet is A, B, C, and you've got a state there, you should have a transition for each symbol in your alphabet, A, B, and C, even if that symbol is not necessarily what you're expecting at that point. And then there are other people, and I'm kind of this ballpark that says, like, just write down the ones you're interested in. So the people that say, like, there has to be exactly one, if you have let's do a very simple state machine here. So if you got something like A, B, so this finite state machine accepts the string A, B. And what happens if you are inputting a string like BB? Well, you start here at the first one and you get a B, and you can immediately see there's no transition for a B. And so you might just say, like, well, that's an error, so the string is not accepted. But some people would say there needs to be a transition for B in there. And likewise, for that second state, there needs to be a transition for A there, because we need to account for that one. On that final one, there also needs to be an A and a B. So what they would say is you need to add a third state here, and we'll call this the error state. And that's where everything that is not needed goes. So here's B, here's A, and here's A, and here's B. And you can see there's no way out of this error state. Once you get to that state, that's it. And actually, the error state also needs to have a transition for everything, right? So it ends up looking like that. So there's no way out of that error state once you get to it. And so here, if you feed in the string BB, and we start at this one here, and you go B, then you get as in the error, and then you go B again, and you end up in an error, and you know the string's not accepted. And if we try to do something like ABA, then here we go A, B, and we get to here, and we go A, and then we go to the error state. So there are some people that say, like, that's the proper way to draw a deterministic finite state automaton. And I agree with them that you need to have all the possibilities kept drawn out there, but it does tend to just kind of clutter up the diagram. And so I'm personally of the opinion that if you don't want to draw them, you can just say, like, well, just assume that any transition that's not explicitly drawn is there going to the error state, and just know that that's what it's doing. So I like to keep my transition diagrams clean, so they're not cluttering up a whole bunch with an error state and all these transitions going to it. So I just like to go with that assumption that if I didn't draw a transition in explicitly, then it's implicitly going to the error state. All right, so a deterministic finite state automaton has at most one transition for each symbol per state. There are non-deterministic ones. Non-deterministic finite state automaton, or NFA. And these can have, I should say, 0 or more transitions for each symbol per state. Okay, so you have a state like this, and then you could have, let's say, A here, a B here, and another A. And maybe even another B. You could have even 3 A's. Yeah, you got more than one. And so I kind of liken this to, you know, I'm not an artist, but here, you're this person here, and you're in this room, and there are 4 doors. So here's one door. Here's another door. Here's another door. And here's another door. And this one's labeled A, this one's labeled B, this one's labeled A, and this one's labeled A. And if you're trying to accept a string that consists of, you know, the symbols of over the set of symbols A and B, you want to wind up in this room, and you're like, well, which of these doors should I go through? Should I mean, if I get the symbol B, obviously I need to go through the B door. But if I get the symbol, and kind of the rules of the game is once you open a door, you need to walk through it. So you're stuck here going, well, which of these 3 doors should I go through? And the only way to really know for sure which of those doors to go through is if you could either look ahead and see what rooms or what states are behind those doors and what choices you have there. And also you'd want to be able to look ahead in the string that you're trying to accept to be able to figure out what's the best choice to make. And that's why this is called non-deterministic, because in a deterministic one, once you make a choice, you go for it. In a non-deterministic, you know, you're going like, well, I don't know which one I should go through. And so the way to solve it is essentially to walk through all of the A doors simultaneously and see where you end up. But that makes it non-deterministic because you're not making one choice. You are making multiple choices simultaneously. So it turns out all non-deterministic finite state automatons can be converted into a deterministic one. And the reason why deterministic ones are important is because we can write a computer program to what's the word I'm looking for? To execute them. So we started a state, you know, you make a choice, you go to another state, you make another state. It's basically one giant if else or giant switch statement to do that. With a non-deterministic, however, you know, it's hard to write a computer program to be able to do little fortune telling to figure out what door is the best choice to make now based upon something that might happen later. And for simple finite state machines, you know, maybe as a human, you kind of look at it and go, well, I can see the next one is going to be a C, so I'm going to walk through the first A door. But what if it's not going to be revealed to you until much later, like maybe 5 or 6 or 7 states later, which of those doors would have been the best at that point? And that's where it gets tricky to write a computer program to do that, because you now have to look ahead quite a ways. And, you know, there can be some very complicated finite state machines. A compiler might have a very, very complicated one to be able to recognize all the things like numbers, variables, keywords, the operators. There could be hundreds of states in that state machine. And you need something deterministic so that the computer always makes the best choice in the room that it's in, and it doesn't have to guess. So let me draw some non-deterministic ones. And I guess I'll just, I'll do maybe 3 states here. So here's my alphabet is A, B. Let's just do A and B. Let's see. Let's label this one A as well. And this one's labeled B. And this one's labeled B. And we'll do an accepting down here, the bottom one. All right, so we can see what makes this non-deterministic is that is on that very first state that you're walking in, there is already two choices. There's two doors labeled A, and you might not know which one is the best one to walk through until you get further into the string. So let's see what are some strings that this accepts. So right here, going down, that's just A. We start here and we can go A, B. That would be a string that we could accept. Let's see, another one would be A, B, B. And another one would be A, B, B, B. 3 B's, I think. A, B, B, B. Yep. Let's do another one. A, B, B. Hey, you just go B, 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 just circling around. So basically, it looks like this finite state machine is one single A followed by as many B's as you need. This one ended up being fairly simple. A, B, 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 B. So the regular expression is A followed by 0 or more B's. So it turns out this one can be reduced to a loop on the B's, and then an accepting state there. So this one here is a DFA, and this one over here on the left is an NFA. So that was kind of trivial to convert this NFA to a DFA. Let's do another one. See, I'm going to maybe need some more states this time. A, B, A, B on that one. And I don't want to get so diabolical with this that I can't even solve it myself. Kind of want to put in one more transition. Let's put it here. There. Hopefully that's not too bad. So the language here is we start here, and then we can go AA. We can do A, B. We can do B, B. B, oh, sorry, let's do B, B. So it looks like a whole bunch of B's and then one last B. So it's a pair of B's. So it's an even number of B's here and then one more. So this bottom route through the machine looks like it accepts an odd number of B's. If I read that correctly, is that right? No. 2 B's. Oh, even number of B's. Got it. So B, 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 and B, 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 6 B's. Let's see. We could do A, and then an odd number of, let's see, let's try again. A, and then B, 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 B. So it's 2 A's and then 3 or more B's. A, and then B, B, B. I'm going to trace that out myself. So A, and then B, 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 3 B's. I could do A, and then 5 B's. But I don't think I can do A and 4 B's. I want to try that out. Can I do A and 4 B's? So 2 A's, and then 4 B's. 1, 2, 3. No. A, 1, 2, 3. No. So you can't do 4. So it's got to be A followed by an odd number of B's. It's kind of cool. Now, are there any strings that I missed? I got AAB, so I'm going to make it like a Z shape. I got AAB. I think that's pretty good. So it's either it's AA or an even number of B's or an AA followed by an odd number of B's. Anyway, well, now I'm curious. Like, can I do the regular expression on this? So what did I say? It's AA, an odd number of B's. So that would be B, and then B, B star, or just an even number of B's. So it would be B, B, followed by B, B star. I think that works. What about BA? Does that work? So we start here and we go B. No, I don't think BA works. We go B, and then there's no A transition here, so we're kind of stuck. And there's no other B coming out of the first transition, so BA doesn't work. Got any other requests? And I got AAB taken care of, yep. And, well, I think that's it. And I'm looking at the regular expression and so I'm going, those first two cases, the AA and then the AABB star, I'm wondering if those can be combined together, but I'm not. They probably can be. Basically, you factor out the AA. Yeah, let's try that. So you got AA, and then you're left with B, BB star, I forgot where I was going with that, so never mind. AAB plus. So someone suggested AAB plus. Now, that's a good suggestion, but this means that this could expand out to AAB, AAB, AAB. So you're repeating the AAB all over and over and over again. And I don't think that's something that this accepts. So we go A, B, and then once you're here at the accepting state, there's no way out of it. So wait a minute, A, B. Oh, look at this, A, B. You're almost right, A, B. But then we have to get over to that accepting state. So you need like AA or BB to get over there. But I do like that AAB is in there. And is that part of what I already have? No, it's not. So that would be something that we also have to consider. That would be a string like AAB, AAB. And then I ran out of space there, but you need more like, another BB or an AA in order to get over to the accepting state. But yeah, there's an AAB in there, which means that another one that we can accept over here is AAB plus, followed by either an AA or BB, but those are incomplete because we need to, oh no, actually, we also said that AAB is an accepting state. Is that right? Let me try this out. So AB, yes, it is. So you see why the non-deterministic ones, you need to be a fortune teller to be able to do this correctly, because I'm taking your requests here and I'm looking at your suggestions and I'm going, well, that doesn't work. Wait, oh, no, it does work, because if you make a different choice at one of those states, then you do end up in the accepting state. But if you make the wrong choice, you end up back in the first state. Well, so what I want to do is I want to copy this and I want to put it on the next page so that my head is not blocking the picture. All right, there it is. And then I am going to number them 1, 2, 3, and 4. And we're going to figure out how to turn this into a DFA. Okay, so I'm just going to kind of give a visual way of doing it. And so you start here at the initial state, the starting state, and we're going to write that one down. I mean, write it down as in draw it. So there it is, state number 1. And then, so imagine we're sitting in room number 1, and we look at all the doors that are available to us. So I'm sitting in room number 1, and I see 2 doors. I see one labeled A and one labeled B. And so I'm going to explore each one of those doors. So I see an A and I see a B. So let's go through. So converting an NFA to a DFA is itself not necessarily really a deterministic process. You're kind of exploring different paths through this graph, and there's going to be some backtracking involved. So you're going to go down one path, and then you're going to get it not necessarily stuck, but you're going to get to a point where you've seen this before. So you're going to backtrack a bit and then go down another path. And so you're kind of fully exploring the entire graph. So it basically takes, what is that, n squared time, n factorial, something like that. Anyway, so we're in room number 1, and we see door labeled A, and it goes to room number 2. And if we follow door B, it goes to room number 3. And at that point, we're completely done exploring room number 1. So now let's explore room number 2. Room number 2, what doors do we see? Well, we see 2 doors labeled A. And instead of drawing it here as 2 doors, I'm going to merge those doors together, and I'm going to make it 1 door labeled A. But as you can see from the diagram, door A leads us to room 3 and room 4. So we're going to consider those 2 rooms to be the same room. So door A out of room 2 goes to 3 and 4. Okay, and then there is no door B on room 2, so we're done with room 2. And now let's go down to room 3. So room 3, we're sitting in room 3, and we see two doors, one labeled B going up this way and one labeled B going this way. So we're going to merge those together and make one door out of it, labeled B, and it goes to 1 and 4. Okay, and I think that's it for room number 3. I only see those two doors. Okay, so now we're going to work on room 3, 4. So consider these rooms to be the same room. And so look at room 3 and at 4 at the same time and figure out what doors you see. Now there's no doors leading out of room 4, but there are two doors leading out of room 3, and those go to 1 and 4. So the merged B door is going to go to 1 and 4, like that. So rooms 3 and 4 simultaneously have one door labeled B going to rooms 1 and 4. And I think that's it for rooms 3 and 4. I don't see an A door there at all. Now let's do 1 and 4. So that's this room and this room together. And what doors do we see? Again, nothing coming out of room 4, so kind of dodged a bullet there. But out of room 1, there is an A going to 3, an A going to 2, and a B going to 3. So an A going to 2 and a B going to 3, like that. And since we didn't add any new states to this diagram, and we've now exhausted all of the doors, all the transitions, we're almost done. We've written out all of the states, we've written out all the transitions, and now we just need to put in the accepting states. And the accepting states are, well, it's a 4 over here in the NFA, so anything that's got a 4 over here in the DFA also becomes an accepting state. So that's this one and this one. So we end up with 2 accepting states. So here's one here, and there's one there. All right, and let's just see if it accepts the same strings. So one of the strings that the NFA accepted was AA. This one does AA, like that. And then let's do AAB, AAB. So that over here in the NFA, that was AAB, AAB. Here in the DFA, it's AAB, AAB. So you end up in this little cycle over here for your AABs. Another one was, what did we say? An even number of B's, was that right? 1, 2, 3, 4. Yeah, even number of B's. So here's 4 B's. 1, 2, 3, 4. And if you want to do 6, 1, 2, 3, 4, 5, 6. What was another one? AA followed by an odd number of B's, if I remember right. It was AA and then 1, 2, 3. There we go. AA and then an odd number of B's in this little loop here. Okay, so every NFA can be turned into a DFA just by following this process. Let's do one more. I think I'll stick with 4 states like I did last time. I'll just make it a little more complicated. Let's see, I guess I'll make this one be an accepting, and I'll make this one be an accepting, and we'll see where we go with that. Come over here. Let's see, let's go that way. Let's go all the way down there. Let's put in a loop there. Notice I haven't labeled any of the transitions yet. I'm just drawing the arrows. So let's go A, B, A, B on this one, A on this one, B on that one, and I feel like I should put in one or two more. We got a comment that says, does the AAB plus not work on the NFA? It doesn't quite work because although, oh wait, no, it does work. AAB plus does work in both the NFA and the DFA. Initially, I thought it didn't work, but once I looked at the NFA long enough, I finally found that path through it. So it does work, but it's not. That is not the regular expression that encapsulates all the possible strings. So it so happens that AAB, those strings do work, but they're not all of them. Okay, so I feel like I should put in something else. And let's just put in another loop right here. Let's put in A there. And what else should I do? Ah, heck. I'll put in a B right there. There. All right. So we want to convert this to a DFA. We're going to follow the same procedure. Oh, let's label them so we know what we're talking about. 1, 2, 3, and 4. All right, we start in room 1, and we go, what doors do I see here? I see 3 doors. 2 of them are labeled A, and 1 of them is labeled B. So I'm going to convert that into 1 door labeled A and 1 door labeled B. Now the one labeled B is easy. That one goes to 4. The one labeled A goes to 2 and 3 at the same time. So I'm going to make a new state and call it 2 and 3. And now I think I'm done with room 1. So let's go and do room 4. That looks easy. So here's 4. There's 2 doors, one labeled B, one labeled A. The one labeled B goes to room 2. The one labeled A goes to room 3. I hope I made enough space here. I'm going to erase this in case I need more space. Okay, so I think that takes care of room 4. I'll say if the entry point is also an accepting state, shouldn't we have a way back to it? No, not necessarily. Although you're right, I probably overlooked that. But what this means with the accepting state also being the starting state means that one possible string that this NFA can accept is the empty string or epsilon, because you can just finish at that point. So that means that if I can write this down over here, the empty string epsilon is one of the strings that this accepts. And then there are others like just A and AB. Is it A, B, 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 B? Yeah. A. Anyway, there's many. But the point is that one of them is the empty string. Anyway, back to our DFA drawing. So I think I'm done with room 4. Now let's go up to the top here, 2 and 3. 2 and 3 simultaneously. So these two rooms, what doors do I see? So I see a door labeled B. I see another door labeled B. Over here, I see a door labeled A, and that's it. So there are A and B rooms. The A and B doors. The A door goes to state 2, like that. And the B door, now there's 2 of them, so we have to consider both of them. The B door goes to 2 and to 3. So essentially, room 2, 3, the union of those two rooms, if you walked through door B, you would end up in either room 2 or 3. So that means that there's a loop here on 2 and 3. And I think that's takes care of 2 and 3. Now let's do just 2. So here at just 2, there's a door labeled A that goes back to itself. And there's no B on there, so we're done with 2. Now let's go do 3. So here at 3, I see a door labeled B that goes to 2, and I see a door labeled B that goes to 3. So from room 3, on a B, we go to 2 and 3. And now I'm going to draw a one that goes all the way around, like that. And there's no A transitions from 3. So I think that's it for all the states and all the transitions. Now we need to put in the acceptings. So this is an accepting. Number 1's an accepting. Number 2's an accepting. So anything with a 1 or a 2 in it is an accepting. So that means this one is, and that one. All right, so let's try it out. So one possible string is just the empty string, and that is accepted here. I need to put on my little arrow. There we go. So the empty string. One of them was just A, which is over here was just that one there. So A, that's an that's good. Let's see, A, B. Over here that was A, B. Here it is A, B. Another one was A followed by a whole bunch of B's. So A, B, 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 done. And then I had 3 A's written down. That's this one here. So A, A, A. There we go. 3 A's. I can see in my diagram. I forgot to label this. And I forgot to label this one. What were those? That's an oversight. So from room 4 on a B that goes to room 2, that should be there. And so this must be an A over here. Okay, so that means in this diagram, B, A, B is accepted. And let's see, does that work in the NFA? It must be this one, B, A, B. Yeah. And then how about B, B, and then a whole bunch of A's? B, B, and a whole bunch of A's right there. What's another one? B, A, B, A. B, A, B, A. Right there. All right. Looks pretty good. Trying to think what we should do next. It's been about an hour, and I've shown some examples of converting NFAs to DFAs. Now we haven't yet talked about the epsilon transitions, and the reason for that is we haven't really covered it in class yet. I gave you a hint about it last class, and that was like we did something like this: X, Y, or Z star. That was a regular expression. And what we wanted to do was draw the finite state machine. And so the inclination was maybe to do something like this. X, Y. That's an accepting. And then Z star, like, do you do this? And then make that an accepting as well. But then that doesn't work because this one accepts ZXY, which the original regular expression doesn't accept. So what I hinted at there was you need some way to get it so that once they start down that Z path, they're stuck there. And so if I draw this out again, we do something like this: X, Y, here's my Z with the loop on it. This is an accepting, this is an accepting, and then there's this epsilon transition there. And so this is non-deterministic also, because you're sitting here in the first room and you don't yet know what, or actually, you get the letter X, let's say, and so you go like, well, I could walk through this door very easily. But there's also this door that's labeled epsilon, which means you could walk through that door without consuming any symbols from the string you're trying to accept. You could walk through that door. You don't have to, but you could walk through it. And that's what makes this non-deterministic, because you're sitting here facing a choice. You're like, should I just go with the X here, or should I go walk through this door and maybe there will be an X transition in the next room, but I don't know that yet because I haven't walked through the door. So it makes it a non-deterministic because you don't know what choice to make. Should you walk through the epsilon door without consuming any letters, or should you immediately walk through the X door and consume one of the letters? And the only way to know that for sure is to know what's behind that door. However, you can convert this into a DFA exactly the same way you did the other one by talking about merging rooms together. So I'll just give you a quick overview of how to do that, and then we'll call it a night. Let's label this 1, 2, 3, and 4. So we're going to start in room number 1. And what doors do we see? Well, we see a door labeled X that goes to room 2, but actually we shouldn't have done that yet. I'm getting ahead of myself. We see 2 doors, one labeled X and one labeled epsilon. And remember, we can walk through that epsilon door for free, essentially. So that means that rooms 1 and 4 become merged together. So instead of just this being room 1 alone, it's actually rooms 1 and 4 merged together. And now we look to see what doors do we have out of rooms 1 and 4 together. I see an X door and I see a Z door. The X door goes to 2, and the Z door goes to 4. Okay, it doesn't go to 1 and 4, it just goes to 4. You can see from this diagram here that if you were in 1 and 4 together, the Z door only goes back to 4. Okay, and now room 2 has a Y door that goes to 3, and then that's it, I think. We need to do room 4. Room 4 has a Z transition that goes back to 4 as well. Okay, and then same thing as before, all the accepting states out of the NFA becomes accepting states in the DFA if they have the same labels on the states. So the accepting states over here were 3 and 4. So anything with a 3 and a 4 over on the DFA side becomes an accepting. So that's the one on the right, the one on the bottom, and the starting state. So over here, XY is a valid string that accepts. 0 or more Z's, so we could just stay right here in the initial state, and that becomes the empty string. We could do 1 Z by going down here. We could do multiple Z's by going zoop, 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 zoop around like that. So this DFA ends up with 3 accepting states, whereas the original one only had 2, but ends up coincidentally with the same number of states overall. Okay, so that's how you handle the epsilon transitions, is that those rooms that are connected by the epsilon transitions immediately become merged together. And it's not just the starting state that happens on. It's any time that happens. If there's an epsilon anywhere, you just merge those rooms together, and then you have to look at all the transitions coming out of it. Okay, so that's about all I want to do for tonight. I hope this helped some of you to answer some of your questions about NFAs and DFAs and give you a recap on what we did over the past week. What we're doing this coming week is I'm going to really show you how NFAs work. So I'm going to throw in epsilons all over the place, and I'm going to give you a much more, believe it or not, a more deterministic algorithm for converting a regular expression to an NFA. It's basically going to be a series of recipes to follow. If you see this, write down this. And if you see this, that, write down that. And then we're going to turn the whole graph into a matrix and then show you how to transform that matrix from an NFA matrix into a DFA matrix. And that's going to cover basically the next week and a half in classes or so. All right. So if there are any more questions on chat, go ahead and post them right now. Otherwise, if I don't see anything in the next minute or so, we'll call it a night. And thanks for joining me.